Okay, so this is a quiz problem I wrote, and I'm going to go over the solution. So let's look at the problem. It says you have a magnetic compass. Oh wait, I have one right here. That is 1 millimeter below a wire. I have a wire that's running north-south. When the wire has current running through it, the compass deflection is 22 degrees. What is the magnitude of the current in the wire? And then what if you moved to a distance of 1.5 millimeters? Okay, so let me show you how this works. If I have my compass right here, this points in the direction of the total, mostly in the total direction of the magnetic field. The Earth's magnetic field right now is pointing that way. It's actually pointing down some too, but this is a weighted arrow so that it will work fine. So let's see what happens if I take a wire. So I have a long straight wire right there, and it's hooked to a battery, but I have a magnet on there, so I'm moving that away. And watch what happens to the deflection of the needle when I connect the battery. So you see in this case, actually I should note that I'm running current this way. Let's flip this around. So now I'm going to run the current this way. So this wire makes a current going in the direction of my thumb. Then the magnetic field wraps around. I'll draw another picture in a little bit. So underneath the wire, the magnetic field due to the wire is perpendicular to the magnetic field due to the Earth. And so if I know the deflection, I can calculate the magnitude of the magnetic field due to the wire if I know the Earth's magnetic field. So let me just draw another picture of this, just so it helps. Or so that it doesn't help. Either way. So let's say that this is the wire right there coming out of the paper. And so the current's this way. Then I'd have the magnetic field due to the wire would look like this. Oops, that's diagonal. Where the magnitude is mu naught over 4 pi 2I over r. Where mu naught over 4 pi is a constant, and that's 10 to the negative 7th. And I guess that would be, what's that, Tesla meters squared coulomb meter per second. I think that's right. Something weird like that. Okay. So if I am down below the wire, this distance r, then I would have the following. I'd have this is the B Earth. This is B wire. And this is B compass. So if they're right angles to each other, then I have formed a right triangle. And if I know this angle theta, then I can say the tangent of theta is equal to opposite over adjacent, so that's going to be B wire over B Earth. And if I know the magnitude of the horizontal component of the Earth's magnetic field is 2 times 10 to the negative 5th Tesla, then I can solve for the wire magnetic field. It'd just be B wire equals B Earth tangent theta. And I'm going to put that in my calculator. I'm going to use Python because I'm a Python guy. So let's hold off on that. That's my answer to part A, though. Part B, what would be the deflection of the compass if I move it to 1.5 millimeters? So if I go right here and I'm down here, how much will the compass deflect? Well, the first thing is to now work backwards. I need to find the magnitude of the magnetic field due to the wire and then use this to find the deflection. So let's go up here. I can say B equals mu naught over 4 pi. Wait, I didn't finish this. This asks what's the magnitude of the current, not the magnetic field. So now I have that. I can say B wire equals BE tangent theta, and that's going to be equal to mu naught over 4 pi 2I over r. Now I want to solve for I. In this case, I call that R1. R1 is 1 millimeter, so 1 times 10 to the negative 3 meters. So if I solve this for I get I equals, I'm going to write this as 1 over mu naught 4 pi. Yeah, I'm going to do that. So that's going to be R1 BE tangent theta divided by 2 times mu naught over 4 pi. Okay, so I'm going to plug this in and get my value for my current. Now for part B, it says, now suppose I move to a new distance and I want to find the new magnetic field and the new deflection. So it's going to be 2 pi over r2. And so I can solve for this B wire, and I'm not even going to put it in. All I have to do is put in r2 equals 1.5 times 10 to the negative third meters. And then I want to find the deflection. So again, I have this. Here's my theta 2. This is B wire 2, B earth. And so tangent of theta is the opposite B wire 2 over B earth. And then I can take the arctangent of both sides. So, the nice thing about using Python here is that I can do this iterative process where I don't actually have to calculate every little thing. If you wanted to, I could take this I and substitute it in for there. And a lot of things are going to cancel. I guess I should do that. Let's say B wire 2 is mu naught over 4 pi. 2, now for I, I'm going to put in all this stuff. So it's going to be R1 B earth tangent theta over 2 mu naught over 4 pi. And then I need to divide by R2. So this cancels, and I can solve for B wire 2. The magnetic field of the Earth doesn't cancel. But now if I put in tangent theta up here, tangent theta is B wire divided by B earth, I get tangent theta is going to be R1 over R2 tangent theta 1. Okay, so I'm going to do it both ways. Let's switch over here to Python because I'm a Python fan. Python makes a great calculator. So let's just start with some constants. Let's say Km, this is the mu naught over 4 pi, is 1 times 10 to the negative 7th, E negative 7. What do I need next? The deflection, theta 1. Theta 1 equals 22 degrees times pi divided by 180. So Python assumes things are in radians, so I convert that to radians. So let's go ahead and B earth. BE equals 2 times 10 to the negative 5th Tesla. Okay, let's just go ahead and calculate B wire 1. BW1, it's just going to be BE times tangent of theta 1. I don't even need to write that down if I don't want to. But now I can go over here and say I equals, I need R1. R1 equals 1 times 10 to the negative 3. And I can say I equals R1 times B wire 1 divided by 2 times Km. And that's the current in the wire. And was that the first question? Yes, so let's print that. Print I equals I amps. Let's just run that. There. So 0.04 amps. Now I want to do the second part, switching over to my work. So the first thing I can do is to calculate B wire 2. So B wire 2 is going to be mu naught over 4 pi, which is this Km, times 2 times I, that didn't change, divided by R2, which I didn't put in there. So R2 equals 1.5 times 10 to the negative 3. Now B wire 2 is that, and I want to calculate the deflection, so I could say, I'm doing this a simple way first. I can say A tangent, theta 2 equals A tangent, which is the arctangent in Python, of B wire 2 divided by B earth. And let's print that. Theta 2 equals theta 2, I want it in degrees, times 180 divided by pi. I'm going to calculate one more way in just a second. So I get 15 degrees. So it's a less deflection because I'm further away. It's less than 22. That makes sense. Now here's the second way I calculated that. Theta 2 equals arctangent of R1 times tangent of theta 1 divided by R2. And let's print that one. I can rename that variable. You can do that. You don't have to make a new variable. I'll just change it. So theta 2 2 equals theta 2 times 180 divided by pi, and let's run that. Same thing. Okay, so there's your quiz, magnetic field due to wires. If you want an extra question, you could say, well, what if I put the compass on top of that? Also, why do you have to have the wire running north-south? The answer is, if the wire is not running north-south, you don't have a right triangle, right? The magnetic field due to the wire and the magnetic field to the Earth may not be at right angles, and then you can't use right angle trig, and that makes your life much more difficult. Okay, that's it.